Today we are going to talk about Hamilton paths and circuits and about complete graphs. So to start with, Hamilton paths and circuits are named for Sir William Rowan Hamilton, an Irish mathematician in the 1800s. Now, similar to an Euler path or circuit, a Hamilton path is going to start at one vertex and end in another, and a circuit starts and ends at the same vertex. The main difference between Euler paths and circuits and Hamilton paths and circuits is that for Euler paths and circuits, we wanted to cross each edge exactly once, and for Hamilton paths and circuits, we want to visit each vertex exactly once. Now, we did have a very nice rule for when Euler paths and circuits existed. If all of the vertices have an even degree, you have an Euler circuit. If you have exactly two odd vertices, you have an Euler path. And more than two odd vertices means you have neither. Unfortunately, knowing whether an Euler path or circuit exists does not tell us anything about whether a Hamilton path or circuit exists. So let's take a look at a few diagrams. So we have three graphs here. First, we're going to look at Euler paths and circuits in these three figures, and then we're going to look at Hamilton paths and circuits. So for figure 1, if I go through and look at the degree of each vertex, all of these vertices have an even degree, so we do have an Euler circuit through this graph. We can trace this picture without lifting up our pencils or retracing our steps and begin and end at the same point. Now, for a Hamilton path or circuit, our goal is to visit each vertex exactly once. So I'm going to decide to start at the top vertex and see what happens. So remember, I'm trying to go to each vertex exactly once. So this blue line goes to each vertex exactly once and begins and ends at different vertices. This is an example of a Hamilton path. The question is, can we create a Hamilton circuit? So I'm going to try again. All right, now I have a path that touches each vertex exactly once, and I can add one more edge to go from this ending vertex back to my starting vertex. And now I have a Hamilton circuit. So this graph has both an Euler circuit and a Hamilton circuit. What about figure 2? If we look at the degree of each vertex, we have exactly two odd vertices, so we know we have an Euler path, and that path would have to start at one odd vertex and end at the other. So what about Hamilton? Can we create a Hamilton path or circuit? Well, I'm going to choose to start at this vertex with degree 1. Okay, here I have a Hamilton path. Let me make a different choice. If I go this way, again, I have a Hamilton path. I do not have a Hamilton circuit. I cannot go from my ending vertex and follow an edge back to my starting vertex. So this one only has a Hamilton path, not a Hamilton circuit. So figure 2 has both an Euler path and a Hamilton path. What about figure 3? Let's look at the vertices and their degree. Again, I have exactly 2 odd vertices, so I do have an Euler path. What about a Hamilton path? Again, I'm going to start at one of the vertices with degree 1. Now, if I choose to go this way, I could go here, and then I'm stuck. If I go this way, I cannot continue because I've already visited this vertex with degree 4 once. If I go this way, I'm also stuck because, again, I've already visited this vertex. I cannot go back to it. So let's try a different route. Go this way. If I go here, I'm done. If I go here, again, I can't go back up to this vertex because I've already visited it. Same thing if I go this way. I can't go back to this vertex. And lastly, if I go this way, I end up with the same thing. Here, I get stuck. Here, I can't continue because I can't go back to that vertex with degree 4. Same thing here. You can keep trying, but this one does not have a Hamilton path or circuit. So figure 3 has an Euler path, but neither a Hamilton path nor circuit. So as I mentioned before, we had some very nice theorems about the existence of Euler paths and circuits that were based on the degree. We have one theorem here about Hamilton circuits, but it's not very useful. This says if a connected graph has n vertices, where n is greater than 2, and all of them have a degree greater than or equal to n divided by 2, then we have a Hamilton circuit. Well, let's go back and look at our figures on the previous slide. Let's look at figure 1. We have 1, 2, 3, 4, 5, 6, 7 vertices. 7 divided by 2 is 3.5. So if all of the vertices have a degree that is greater than 3.5, so in this case 4 or more, then we know we have a Hamilton circuit. Well, some of the vertices have degree 4, 2 of them only have degree 2. But we still have a Hamilton circuit here, even though it does not meet the criteria in the theorem. So here's why this theorem is only somewhat helpful. We know that if there are a lot of edges, so you have vertices with a large degree, then we have a Hamilton circuit. But this theorem tells us nothing about what happens when we don't have a big enough degree on every vertex. So yes, if every vertex has degree of n over 2 or more, we have a Hamilton circuit. But if the degree is less than n over 2, we know nothing. We might have a Hamilton circuit, we might not. So sometimes we know that a Hamilton circuit exists, other times we don't have enough information. So that's the first part of this. The second thing I want to talk about today is the idea of a complete graph. So if you have a graph with n vertices, and every pair of distinct vertices is joined by an edge, that is called a complete graph. So in other words, every vertex is connected to every other vertex in the graph. and we use the symbol k sub n. So k sub 4 would be a complete graph with 4 vertices. K sub 72 would be a complete graph with 72 vertices. Now, we have a nice little formula to figure out how many edges are in a complete graph. And that is just n choose 2. Or if you remember back to your combination formulas, n choose 2 is the same as n times n minus 1 over 2. The other thing that we know about complete graphs is if we're only looking at simple graphs, meaning we have no loops and no multiple edges, a complete graph has the most edges. So for example, the complete graph of 4 vertices has 6 edges. So a simple graph with 4 vertices can have at most 6 edges. So here we have the graph K6. We have 6 vertices. Typically they are arranged in a circle, or in this case on the corners of a hexagon. And then we have each vertex connected to every other vertex in the graph. And if we want to know how many edges are in this picture, we just need to do 6 choose 2, which is 15. And you can try to count the 15 edges here. We have 1, 2, 3, 4, 5, 6. I apologize for my drawing. 7, 8, 9, 10, 11, 12, 13, 14, 15. If we want to know how many edges are in K30, that would be a lot harder to count on the picture. But we can just do 30, choose 2, which gives us 435, which is a lot of edges. So now let's take a look at Hamilton circuits in a complete graph. So there are n minus 1 factorial distinct Hamilton circuits in the complete graph of n vertices. You might be asking, what do we mean by distinct Hamilton circuits? Well, we'll get to that in a second. How many distinct Hamilton circuits are in K4? Well, we have 4 minus 1 factorial, or 3 factorial, which is 6. And we will come back to this example on the next slide. What about in K11? 11 minus 1 factorial is 10 factorial, which is 3,628,800. So let's go back to what do we mean by distinct Hamilton circuits? Well, here we have the graph of K4. We have 4 vertices, A, B, C, and D, and each vertex is connected to every other vertex in the graph. So one Hamilton circuit would be A, B, C, D, A. But why did I choose to start at vertex A? Just because it's the first letter in the alphabet? What if I started at vertex B and went B, C, D, A, B? What if I started at vertex C? C, D, A, B, C. Or what if I started at vertex D and went D, A, B, C, D? All 4 of these, I am going out around the outside of this graph in a clockwise direction. So these are not distinct. They are technically the same circuit. with a different starting point. So, on the previous slide, when we said that there are 6 distinct Hamilton circuits in K4, these are not distinct. These are all the same circuit. So what do we really mean by distinct? Let's take a look at this same graph of K4. So we already said that we could do A, B, C, D, A. That is one circuit. We are starting at A and going around the circuit this way. Now let's list out all possible circuits that start at A. We have this circuit. We also have its mirror image, meaning we could go the other direction around the square. We could go A, D, C, B, A. Well, so far, these are 2 distinct circuits. We could also go A, B, D, C, A. A, B, D, C, A. Or we could go in the opposite direction. A, C, D, B, A. So now we have 4 of our 6 distinct Hamilton circuits listed. Lastly, we could go A, C, B, D, A. A, C, B, D, A. Or the reverse, A, D, B, C, A. So you can see here, we have made 3 different shapes: the square, the hourglass, and the bow tie. And we can go in 2 different directions for all of those circuits. So these are our 6 distinct Hamilton circuits for K4.